So we discussed numerical data. Numerical data. More than two groups. Independent. They can be also dependent and paired, but this we didn't include. Independent. This the classical test here is one way, a parametric test. Parametric test is one way alone. ANOVA stays for what? ANOVA, analysis
of variance.
Analysis of variance, yes. Parametric, which has some assumptions, namely assumptions of ANOVA.
The same with others. Normally distributed and
sample size.
Sample size and
homogeneity.
Homogeneity of variances. And what did you say? Normal distribution. Okay. These are the three classical assumptions for parametric tests, which applies also for ANOVA. And we also learned a test, a name of a test to be done.
Bonferroni.
Bonferroni, what was the test which was checking for the homogeneity of variances? Starts with L. Okay. Levene's test. And yes, if you cannot meet the assumptions, the non-parametric alternative was?
Kruskal-Wallis.
Kruskal-Wallis. Okay. So, what was the example? Classic, in any scenario for doing an ANOVA or numerical data more than two independent groups. We need a numerical data. We want to compare what? Weight. What?
BMI.
Again, BMI, yes. Did you say BMI?
Yes.
Okay, very good. BMI, compare BMI. Compare BMI between, of course, the mean BMI. We want to compare the mean BMI between what? You need more than two groups.
Ages, different ages, maybe.
Yes.
Maybe between class 2, class 4.
Yeah. Class 2 and class 4, okay. This is two groups. We need more than two groups.
And class 3.
Class 3, yes. Between different classes. Between different classes. Okay. That's good. Yeah, if you have this scenario, compare BMI and numerical data between different classes, more than two groups. Okay, or compare body weight, height, blood glucose between more than two groups. Any more than two groups can apply. Age groups, disease categories, countries of origin, yeah, all more than two groups. So one problem with the numerical data more than two groups was, if you find it significant, if the p-value is less than 0.05 and you decide that there is a significant difference difference between the classes, you want to go and check which classes make the difference, right? Because the ANOVA tells you only, gives you one p-value, tells you that there is a significant difference between the classes. But you want to know if there are three classes, class 1, class 2, and class 3. If ANOVA tells you that there is a difference, you will ask, is there a difference between class 1 and class 2? Or between class 1 and class 3? Or between class 2 and class 3? There will be 3 more hypotheses to be tested. This we call what? Check for these 3 tests. There's the post-hoc tests. Do you remember post-hoc? And among the post-hoc comparisons, we had the classical post-hoc comparison, Bonferroni. What was Bonferroni? Anybody remembers Bonferroni? It looks like an Italian name.
Is it showing like, is it showing all? Like it shows the detail.
It shows the detailed
of multiple
comparisons. Yeah.
comparison.
Sorry?
Multiple comparison.
Yeah, it makes multiple comparisons. This is multiple comparisons. The ANOVA makes a single comparison. One-way ANOVA makes one comparison, gives you one p-value. One p-value here. But while the post-hoc comparisons gives you 3 different p-values, or as many as you have groups. If you have 4 groups, it will be more combinations, of course. So multiple comparisons, yes. Bonferroni is for multiple comparisons. But how was it calculated? There was a simple rule. Because you have, the problem is with the Bonferroni, you increase in the post-hoc comparisons, you increase the alpha error. No?
Yes, alpha.
Post-hoc comparisons, comparison increases alpha error because you have 1, 2, 3 alpha errors instead of only 1 alpha error in the ANOVA. So to deal with this increased alpha error, we make the Bonferroni correction. How do we correct? Multiply.
Reducing the 95%.
No. Multiplied p-value multiplied by the number of tests, number of comparisons. So if you have 3 comparisons here, each p-value you multiply by 3. That was Bonferroni. You remembered? Okay, it looks like you never heard about it, Bonferroni. Yeah? You want me to show it once more? Analyze. Compare means one-way ANOVA. I want to compare age. This is a numerical variable between the different occupational groups. There are more than 2 occupational groups. And here I have post-hoc comparison. Among the post-hoc comparisons, there are many methods to make post-hoc adjustment. First, post-hoc comparison. Bonferroni is the classical one, we said. If you click Bonferroni, you click OK. You will have an ANOVA table This is the ANOVA showing the difference between the, let me show the descriptive options, descriptive variable, and of course homogeneity of variances we need to check, because homogeneity of variances was one important assumption. Okay, we have here the different categories of occupation, professional, technical, housewife, etc. And here are the means, mean ages, 52, 54, 53, 66. And ANOVA seems to be significant. ANOVA seems to be significant. P-value is less than 0.05. And here we have the post hoc Bonferroni. Also, Bonferroni makes multiple comparisons between professional and technical, p-value 1, professional and manual 1, another p-value, professional retired, significant, professional others, significant, and so on. Okay, but actually we don't meet the assumptions. There were three assumptions here, 1, 2, and 3. Normal distribution we didn't check, but we don't meet that sample size and the homogeneity of variances. You see the sample size? We have groups with only 3 samples, students, only 3 students. So we should not conduct the ANOVA. If you have this kind of question, do we meet the assumptions? You will say no. First of all, we don't have enough sample size. And second, do we meet the homogeneity of variances, Levene? Are the variances here homogeneous? Can somebody answer this question? Are the variances here homogeneous?
No, I think.
They are not homogeneous. They are significantly different. These variances are different. Why you'd say they are different? Because
It's below 0.05.
Thank you. Yes. Thank you. You are great, my boy. Yes. Because the p-value here is less than 0.05. In fact, when I see the standard deviations, this students group has a very low standard deviation, while the others have around 10. Okay, and the other test was McNamara last time. We discussed also McNamara. Where do we use the McNamara?
If there is an error in the assumptions?
No, this is finished. The numerical data more than 2 independent groups is finished now. Last week, we discussed.
Nominal, paired nominal data.
Yes, thank you. We have 2 groups, 2 measurements paired. 2 repeated measurements, repeated, which means paired or dependent. Measurements, 2 repeated measurements for a categorical data. Okay. Discard. Today, I'm going to explain you categorical data to independent groups. Which test? Which test is that? This is the most commonly. Categorical data. What's that t-test? Okay. Categorical data, independent groups. Doesn't matter, only 2 independent groups or more than 2 independent groups. if you have categorical data, independent groups, you do the chi-square test. Chi-square. And this is the Greek letter chi. It's a Greek letter. It looks like X, but it is not X. Chi-square. Chi-square test. Okay, let us read from the book. What is this chi-square? Categorical data, two proportions, or even if you have more than two proportions, two or more than two proportions, you do the chi-square test. Chi-square test. For this chi-square test, you have the contingency tables, like 2 by 2 table, because if you have categorical two proportions, you will have a 2 by 2 table, but it can be more than 2 by 2. These are the contingency tables or cross tabulations. So the classical tables are this here, cross tables. If you want to make chi-square, you must have categorical data and this kind of cross tables. You may have, usually, the classical approach is that you have the dependent variable in the columns and the independent explanatory variables in the rows, but doesn't matter. So here we have, for example, disease status, disease, positive, corona, for example, no? Positive, negative, corona, let's say it's corona. And we want to compare corona in two independent groups or more than two independent groups. Is it more common among males or females? Is it more common among Kyrgyz students, among Kyrgyz people, among Pakistani people, among Indian people, among Turkish people? Two groups or more than two groups, independent. Okay? So let's say it is, it is the country of origin. Kyrgyz, Pakistani, Indian, or Turkish. Okay. You have three groups now. Three independent categories and one categorical outcome variable. Disease, positive and negative. As you see, we will have, let's say we have a total number of participants in this study. The total number shall be, I want to make it easy, okay? The total number is, general total is, let's say 100 participants. We have 100 participants total. If you have total 100 and 10 of them have the disease, 90 doesn't have the disease. And those 10, let me distribute them. They are 3 Turkish, 3 Pakistani, and 4 Kyrgyz students. Those who don't have the disease, its total is 90. So this I'm randomly distributing. I'm just making up. I'm just making up. This is the majority shall be Kyrgyz. Okay, this is 50. So 54. This is 20, 50, 70, and this is 20. So the total now makes 100, okay? The question in chi-square is, you have the observed values. These are your observed values. but you have also some expected values. Because if I have 100 total 100 students, and then I would have some expectation how many of these total, if 10 of them have the disease, how many of the Kyrgyz students should have the disease. That would be the expected value. So you have to, in chi-square, you have the observed, and expected values. The chi-square test relies on the observed and expected frequencies. Let us see. Here is the formula. The chi-square calculation is based on the observed minus expected. This minus 1/2 is a continuity correction. It doesn't make much difference. Important is that you remember it is based on the observed minus expected squared divided by expected values. So observed and expected values. This is making the chi-square. I will do an SPSS example to show you. You have done, I am sure in your projects, you have done many chi-square tests. It is done from analyze, descriptive statistics, and crosstabs. Here we have. So the column should be the dependent variable, usually. Let's say smoking status. Smoking status is the dependent. And sex, let's say, is my independent variable. I want to see whether there is a significant difference between the males and females concerning smoking status. You see the counts I have here, observed and expected. First, let us see the observed ones. Click continue, and statistics, I want to see the chi-square. Continue and OK. OK. You see males, females. I have 220 males and 187 females. The total number is 407. From the males, 33 are smokers, yes, and from the females, only 1 is smoker. So these are the observed values. In fact, if you have 407, and from the 407, 200 and you know that 220 are male, and there are 34 total smokers, then you could make a calculation. You could make proportions and calculate how many of the males are expected to smoke, right? If out of 407, 34 are smoking, then let me write it in this here. If I have 407 total and 34 smokers, then I would say how many of the 220 males are smokers. 220 males, how many are smokers? And then the calculation would be question mark is equal to, how do you calculate it? 220 multiplied by 34 divided by 407. So this would be my expected value. You can calculate it with the SPSS. Let us do this SPSS analysis again. Descriptive statistics, crosstabs, cells. As you see, I can select expected. Let the SPSS do this calculation for us. You see now I have observed and expected values. Why I did this exercise, all this writing here, to show you how they calculated the expected values. The computer calculated the expected values based on the total number. Total number is 407. Out of these 407, 34 are smokers, which means that from the 220 males, 18.4 are expected to be smokers. Instead of 18.4, we have 33 different. Out of the 187 females, how many are expected to smoke? 15.6. Instead, we observe how many? We observe only one. There seems to be a difference. So the calculation here would be, the chi-square would be equal to, you remember the formula? Observed minus expected divided by expected. So let us calculate it. The first cell observed is 33 minus expected 18.4. 33 minus 18.4 squared. I'm omitting the minus 1.6. This minus 0.5. I am omitting it. Divided by expected. Expected is 18.4 plus as many as cells as I have. I have to do this calculation because you see there's a sigma here. Sigma means what? Calculating all the possible combinations. The second cell is this one here, 187 minus 201.6. 187 minus 200, what was it? 201.6 squared divided by 201.6, and I continue to do this for the cell number 3 and cell number 4, and at the end I will have a chi-square value which is 27.6. 27.6. You see, there is in SPSS gives you another chi-square value with the continuity correction. If you have continuity correction, it means you have in the formula this minus 0.5, minus a half. If you don't have this in your formula, you will have this classical chi-square. For large sample sizes, this is not a big issue because they will be very similar. You see 27 and 25. Both have the same p-values. But if you have small sample size, then you should do the continuity correction. Okay, so this is how they calculate the chi-square value. After you calculating the chi-square value, since we know the propensity distribution formula for the chi-square distribution, the theory distribution, we compare our value with this theory distribution and we find a p-value. In this case here, the p-value is significant. We had an opinion that it would be significant because the observed and expected values are very much different from each other. Okay, are you following me? If you don't follow me, please ask me to repeat it.
Yes.
Okay, so this is how you calculate the chi-square value. And yes, but there is one rule for the chi-square. This is not because these are non-parametric tests. We don't have the assumptions like normal distribution or sample size. But the chi-square has a one. The chi-square has one assumption, which is the expected values. The expected values should be more than 5. Here is the rule. There is one rule, the rule for one rule to do the chi-square. Less than 20% of the cells What are the cells? These are the cells. Cell number 1, 2, 3, 4, 5, 6. I have 6 cells here because 2 outcomes, possible outcomes, and 3 categories. Less than 20% of the cells should have or may have expected values of less than 5. This is the rule. This is the rule for doing a chi-square test. And automatically at the end of the table in SPSS, you see a report that 0 cells, because all the cells have expected values more than 5. You see 18, 200, 15, 170, or are above. So no cells have expected counts less than 5. Let me do this again so that we will have some expected values less than 5. Cross tabs, smoking status again, not sex. Instead of sex, I will have something else here, educational status, let's say. How is it with the educational status? You see, if I compare education status, non-primary school, intermediate school, secondary and university and above, 2, 3, 4, 5 categories. If I compare smoking status between these 5 categories, I have expected values of 17, 197, 79. Aha, here is one expected value which is less than 5. 3.9. There is another expected value, second one, 3.4, and another expected value less than 5. So 3 expected values, 1, 2, and 3, are less than 5. 3 cells, which makes 30%. Why 30%? Because 2 by 5 makes 10 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cells. I have 10 cells. Out of these 10 cells, I have 3 which have expected counts less than 5. So it makes 30%. But my rule was what? 20%. Maximum 20% of the cells may have expected values of less than 5. So if I exceed 20%, if this is more than 20, then it means it is impossible. It is not possible to do, it is not safe to conduct the chi-square test. Instead of the chi-square test, in this case, I should do what?
Cross columns.
Pearson correlation.
No. It starts with F.
Fisher exact test.
Fisher
Thank
exact?
you. Yeah. Fisher's exact test. Okay. So chi-square, always remember chi-square with Fisher exact. You do the chi-square, normally you prefer to conduct the chi-square test. But if there is one rule with the chi-square, the cells expected values, expected of course, not observed, expected values should be above 5, 5 or more than 5. If you have more than 20% of the cells which have expected values of less than 5, it is not possible to do the chi-square. then you go and you conduct the Fisher's exact test. But there is one more issue. The Fisher's exact test is done classically, it's done for a 2x2 table. Here you see the SPSS is not reporting the Fisher's exact test. But if you do a 2x2 comparison, like smoking status compared between male and female, then you see the computer gives you the Fisher's exact test. Fisher's exact, it is the same in this case. And you don't need the Fisher exact here because you don't have the violation of the expected counts. But here you have the violation of the expected counts and the computer doesn't give you the Fisher exact. What is the solution? The solution is you may combine the groups, yeah? You may merge the groups. You may merge secondary university together. You may merge, you may combine some of them. You may decrease the categories. By this way, you may get rid of the low sample size in the groups. Okay, or the other possibility is the SPSS also calculates you the exact values in the larger groups. For steps, we have here the exact option. If you select the exact option, then, but it's not possible for some calculations because this requires a lot of processor capacity. So sometimes it's not possible to do the exact test, but here it worked, you see. We have the Fisher exact test. So since 3 cells, more than 20%, have expected counts less than 5, I should read here the exact test. And the significance value for the exact test is 0.001, not 0.000. Could you follow me? That's all. That's all about the chi-square test. So independence groups, we have the chi-square test. If it is paired, we have the McNamara test. This we discussed last week. And if you have more than 2 categories, categorical data, more than 2 categories, it doesn't matter. Even then, you have to go and do the chi-square test again. But in the chi-square test, at least 80%, this is from the opposite side, at least 80% of the expected frequencies should be greater or equal to 5. This is the only one assumption for the chi-square. If you don't have this chi-square assumption, then you do the Fisher's exact test.
Sorry, sir. Can I ask a question?
Yes, please.
Sir, you said we should change it if it is more than 20%.
Yeah. The one solution is you can merge, change. By change, I understand you merge the groups. You combine the secondary and university. 5 plus 2 makes 7.
What if my result is like 12 cells, 85.7%, less than 5%?
If too many of them, you mean, yeah, then you have to, the only option is you have to ask the SPSS, as I did here, to give you the exact test in your original data without changing. It is possible. Without changing the groups, SPSS allows you to combine, to calculate the Fisher's exact test. But otherwise, you may join them. You may say, okay, Kyrgyz is one group, Pakistani plus Turks, I will have combined them. You may combine them, then you will have 2x2 table. Kyrgyz, Pakistani plus Turks plus TR plus Turks. You will have a 2x2 table then. But of course, combining Pakistani and Turkish would have no sense you would have be criticized for that. You should make rational merging. Here, it is not rational. There is no logic behind merging these groups. How are we with the time? Oh, I already finished my time. Okay, time is up. Let us have a short break, then continue with the correlation. Dr. Are we ready? Are you ready for the last session?
Yes.
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 Okay. Then let me go ahead with the correlation and regression. I decided to mention about correlation and regression in the same session and finish, hopefully, by this way, all our theory classes for this course. So I will start with a graph here. Okay, if I have this graph, this is the y-axis, this is your x-axis, and this is your line. From your math sessions, this is A, let's say. The point here is A. The function of this graph, fx, would be what? Equal to, do you remember from your math session, math classes in the high school? How do you calculate the function here? How do you formulate the function here?
Slope 2 minus slope 1.
Fx is equal mx plus y.
That this is A here. A is where the line crosses the y-axis.
We use
A,
formulas there, maybe.
yeah, A plus y multiplied by the slope of this curve, which is r. Y multiplied by r. This is the formula, right? Did you remember the formula from the high school? No?
Yes, I remember it.
Yeah, thank you. Yes, well, I'm sure you all of you had this in the math classes in the high school. It's a very simple formula: a plus y multiplied by r. R is the slope of this this line, and r can have a value from what are the values for r? R can be between -1 and +1. Do you remember that? And R, let me show you an R of -1. R of -1 would be looking like what? should be minus, huh? This is an error of -1. As x is increasing, y is decreasing, or as y is increasing, x is decreasing. Reverse relationship. Or if you have a +1, +1 is what? This one is +1. 45 degrees. 45 degrees perpendicular the line. Okay, this is +1. R +1, R -1. Okay, and it can have any value in between. For example, if I show you this graph and my line is parallel to the x-axis, it would be, what would be the R? R here is 0. R is 0. Okay, so let's go to the book. Let's go and seek help from the book. You see, an arrow of +1, an arrow of -1, and you may have also R values where it is plus, but not exactly 1. It is a little bit scattered. By the way, do you remember the name of this graph? What was the name of this graph? We discussed 5 different graphs in our class with you.
This is positive.
No, the name of this graph. If I want to do this graph with SPSS, I will do analyze, graphs. Which graph is this?
Category scatter.
Scatter, thank you. Yeah, it is scatter. These are called the scatter graphs. Huh? Scatter. Okay. So, what is the difference between correlation and regression? In correlation, I look. By the way, both correlation and regression apply for which kind of data type?
Numerical.
Yeah, exactly. Congratulations. Thank you. Yeah, numerical data type. It should be 2 numerical data, numerical and numerical. Between two, you want to compare 2 numerical data. Can it be also a numerical data and an ordinal categorical data? Yes, it can. Ordinal. You can have also compare. You can also do a correlation analysis with a numerical data and ordinal. This is for, of course, correlation. Correlation. Here you can do the correlation analysis. But if you want to do a regression analysis, you need 2 numerical data, numerical and numerical. Okay, what is the difference between correlation and regression? In correlation, we look and we just mention, is there a relationship? Is there a relationship between the 2 variables, x and y? Is it increasing as one is increasing? Is the other one decreasing as one is increasing? But in the regression, we try to find a formula and calculate one value based on the other one. So the main difference, what is it? If I ask you, what is the difference between correlation and regression? You will say what? In regression estimates, tries to estimates a variable based on the other one. Okay. In correlation, on the other hand, in correlation, you don't have an estimation. You don't try to estimate. You just look and say, is there a relationship or not? If there is a relationship, you say the slope, the strength of the relationship is 1, -1, or 0, or whatever. So in this case, this formula applies only for regression. This formula, because in this formula, you are making an estimation. You are trying to estimate x based on y. Okay? This is the main difference between correlation and regression. It is very simple in the beginning. If you look at the beginning, it's very simple, but there are some rules, of course. How to calculate the R, I will not ask this. I don't think it is easy to remember for you. There are instances when this correlation is void. This correlation is not possible to calculate. You should not go and calculate an R value, because imagine if you have a relationship, but it is not linear, as it is in this curve. There can be a relationship, but it is not linear. It is curved. It is exponential, as it is in this example. Or you have outliers. It is here. You have outliers. Or you have accumulation of the data in different areas, as it is in this figure here, to distinct groups. Then, of course, it is not logical. You should not calculate the R values. It's impossible, you can imagine. R is only possible to calculate if you have a linear relationship or semi-linear, scattered dots, but they are not extreme values, no outliers, and no accumulations in subgroups. Here we have two different subgroups. It is not possible to calculate the Pearson. This is the Pearson, by the way. You have two different Pearson. You have two different correlations. Two different correlations. One is the Pearson, and the other one is the Spearman. Spearman. When do you do the Pearson? If you have a linear relationship and no outliers, linear relationship and no outliers, and then you can do the Pearson correlation analysis. If you have one ordinal data, one group is ordinal, then you do the Spearman. Or you have outliers, you do the Spearman. So Spearman, in a way, is the non-parametric. Non-parametric. And Pearson, we can call it the parametric. Okay? Using the terminology parametric and non-parametric, we can decide that Pearson is a parametric test, while the Spearman is a non-parametric alternative. Let me calculate. So, analyze, correlate, evaluate correlations. I want to compare and see whether there is a relationship between weight and height. These are my two variables. I want to do a Pearson correlation because I have checked, let's say I have checked and I have seen that I don't have extreme values. I don't have outliers, and the relationship between weight and height is linear. I assume a linear relationship. Here is my outcome, computer output. I have a p-value, significance, and an r-value in the correlation analysis. A p-value and an r-value. The p-value shows me it is the correlation between the groups is significant, or the r-value is significantly different than 0. If r is 0, there is no correlation. Remember? R is 0, no correlation. Okay? Yes. By the way, this is not 0, of course. R0 means there is the dots are randomly distributed. There is no correlation at all. Okay, so if you have an you have two computer outputs. One is the R value, and the other one is the P value. P shows you whether there is a significant whether the correlation is significant or not. R tells me whether the correlation is positive or negative, and is it a strong correlation or a weak correlation. If there is a strong correlation, I should have a high R value, of course. Let us do the scatter graph, scatter dot, and see. Where is my weight? Here, and height, x-axis and y-axis. Click OK. This is my scatter dot here, scatter diagram. I can include the slope elements, fit line. You see, now I have the slope. Let us see the R value here. The slope is, you see the formula, minus 26 plus 0.63 multiplied by x. This is the slope of my formula. Huh? Okay, so this is the regression formula, actually, the regression formula. So the R square is here 0.14. R was 0.37. So if you multiply it, take the square of 0.37, it is 0.14. Yeah, this is how it looks like, the scatter dot and my correlation analysis. Okay, so if I have two numerical data and then I can go and calculate the Pearson error. But if one of the variables is ordinal, if at least one variable or both are ordinal, they are not normally distributed, the sample size is small. These are all the the assumptions of the parametric tests. Then I go and I calculate the Spearman rank correlation. You see, rank is what? It is non-parametric. It's showing that it is non-parametric rank correlation. It will give me very similar output. Let us do the same exercise with the correlate, bivariate with the Spearman as well. So Pearson and Spearman, to compare their how they look like, they will be very similar. You see, here is the Pearson correlation and Spearman correlation. Pearson is 0.37, the R value. For the Spearman, it is 0.39, and both are extremely significant, 0.00, less than 0.001. Also, the Pearson is less than 0.001. So the correlation coefficients are most of the time very similar, and this 0.3 means it is not a strong correlation, but there is a significant correlation between body weight and body height. And it is positive, of course. As height is increasing, also weight is increasing. So this much, I think, is enough about the correlation. From correlation, you should remember what? You should remember there are two types of correlations: Pearson, which is parametric, and Spearman, which is non-parametric. And what else you should remember? The correlation analysis gives you an R value, which is showing the slope of the curve, of the line. And it can be between -1 and +1. It can be made between -1 and +1. And -1 means there is a negative, minus means there is a negative relationship. And if it is plus, it means there is a positive relationship. And if it is significant, you can decide that there is as body height is increasing, so increases the body weight. Let's go and do a regression analysis. A regression analysis, we have the linear regression here in the SPSS. In the regression analysis, you are trying to estimate a value. Please remember, in a regression analysis, the difference between correlation and regression, in a regression analysis, you are trying to estimate a variable. So which variable I would like to estimate? I would like to estimate the body weight. I want to estimate the weight based on which variable? Based on the height. Based on the height. As you see, in a regression analysis, there can be more independent variables here, but because this is a simple class here, basics of regression, we will have only two variables, one dependent and one independent variable. Okay. You can have the plots here if you want, but let's omit this. We already have the regression and the correlation analysis. Let me click OK and see what I have. In a regression analysis, I am building a model. You see the R here, 0.37. It is the same R value as calculated in the Pearson correlation analysis, 0.37. So the R value you have. And then you have a formula. This is the formula for the regression formula to estimate the body weight. How can I find the body weight? By using this formula, -26 plus this constant here, 0.62 multiplied by height. So if I want to write down the function of body weight would be equal to -26.05 plus, because this constant here, this is plus 0.628, 0.628 multiplied by 8, multiplied by body height. Okay, Is it a reliable formula or not? It gives the answer is depending on the R or R square. The R square here is 0.14, so 14%. This we have seen also in the graph here, the correlation graph. You see, the R square is 0.14, which means 14% of the dependent variable can be calculated based on the dependent variable. And here is my formula. Y, which means the weight, body weight, is equal to minus 26 plus 0.6 multiplied by body height. Okay, this is the formula. So in summary, I think that much should be enough for you. In summary, correlation and regression are brothers and sisters. They are very much related with each other. But in a correlation, you only look, is there a relationship between the two variables or not? The relationship can be negative or positive, or there can be no relationship at all. If R is 0, there is no relationship at all. Instead, on the other hand, in the regression analysis, you try to estimate one variable depending on the other one. And you come up with a formula, the regression formula. The simple formula is fx a plus y multiplied by r, and the SPSS or the calculation gives you a constant and a multiplier, and by this way you can calculate, you can try to estimate your dependent variable. Of course, your estimation will not be precise. Why it is not precise here? Because the R value for this example here, the R value is not so high. The R is 0.37. So R here is, let me write it down here, R is 0.37. If I show you this R value in the exam and I ask you, what kind of relationship do we have here? You should say it is a positive relationship, first of all. So as one variable is increasing, the other one is increasing as well. A positive relationship. And it is not strong. It is weak correlation. Because it could be the maximum values are -1 and +1. This is around 0.3, is less than 0. The half of it, the half of the absolute value. So it is a weak correlation. So your answer should be a positive, but weak correlation. Okay, a positive but weak correlation. Is it significant or not? For this, we look to the p-value. Yes, it is significant. So the relationship, the correlation is significant. P is less than 0.05. Significant. There is a significant but weak correlation. Significant but weak correlation. And if you want to go further and do a regression analysis, and this regression analysis will allow you to estimate one of the variables based on the other one, and it gives you a regression formula. Wow. Enough? I think that's enough.